One of the applications of acetals is that they can be used to protect aldehydes and ketones in a multi-step reaction. So let's say maybe we had a reaction that had a couple functional groups on it, and one of the functional groups was an aldehyde or a ketone. And we wanted to do a reaction on a totally different functional group, but we wanted to leave that aldehyde or ketone alone. We didn't want anything bad to happen to it. We could protect the aldehyde or ketone, do the reaction to the other functional group, and then deprotect the aldehyde or ketone, and it would be left intact and unreacted. And so we're going to look at an example of how that works. So in this first reaction, right here, what you're looking at is just the overall plan of how we protect and then deprotect, in this case, a ketone, but you could do this with an aldehyde. Usually when we're trying to do a protection of an aldehyde or ketone, we use this particular diol. This is a molecule that has two OH groups. So this molecule right here by itself is serving as the 2-ROH that's needed for the formation of the alcohol. We just have both of those OH groups on the same carbon chain, but it works the same. So you see we've got our acid catalyst present. And when we do the very first step in this reaction, the diol gets added to the ketone. And what I'm doing is highlighting the parts that came from the alcohol, and I'm also going to highlight in a different color the parts that came from the ketone. And we call this a protected ketone because the ketone functional group has been temporarily converted into an acetal. The formation of the acetal is a totally reversible reaction. So if we want to convert the acetal back to the ketone or aldehyde, all we have to do is put a little bit of water in there, acidify a little bit, and then we return it easily right back to the ketone or the aldehyde that we started with. Here's an example of when we would use this. This is used a lot when we're trying to do Grignard reactions with molecules that have multiple carbonyl groups in them. Grignards are reactive towards all the carbonyl groups, aldehydes, ketones. This is an ester that we have here. So their Grignards are going after all of the carbonyls. And if we look at this particular reaction, the molecule that we're trying to make over here, you can see that we want the ketone to be left alone. We don't want anything to happen to the ketone. We want the ester to be converted into an alcohol. So we want to do a Grignard reaction on the ester and not have the Grignard affect the ketone. So the way that we're going to do this is start by protecting our ketone, and we're going to use that same little diol because it's a perfect protector. The aldehydes and ketones are the only carbonyl groups that will form an acetal. So notice here it says carboxylic acids and esters cannot be protected by acetals, even though they have a carbonyl group. They won't do the protection reaction. So this is going to selectively protect the ketone, and temporarily it's going to look like this little thing right there. And then once we get the ketone protected, we can go ahead and do the Grignard reaction. In the Grignard reaction, you can see that we are trying to add to the carbonyl carbon. We want to put two methyl groups on it. So that means that the Grignard that we want to use needs to be a methyl Grignard, CH3, MgBr. We're adding two of them, so we need a lot of that. We'll say we need excess, and that's going to be in step 1. And if you recall, in Grignard reactions, we always have a step 2 water or step 2 H3O+. That's required in the Grignard reaction. that step 2 water, or step 2 H3O plus, simultaneously is serving as this deprotection step as well. So not only does this finish up the Grignard reaction, it also automatically deprotects our aldehyde or ketone, and boom, that's perfect. We end up with the alcohol that we're looking for, conversion of that ester functional group, and the ketone is left alone.